Okay, next we're going to look at assessing ventilation. We want to talk about respiratory volumes and respiratory capacities. Respiratory volumes can be measured with a spirometer. And a spirometer used to be a very large, cumbersome clinical tool, but now we have electronic spirometers, and those are the devices used today. Some of our respiratory volumes include tidal volume. Tidal volume is just normal breathing, a normal breath in and out. It averages about 500 milliliters, whereas inspiratory reserve volume is the amount of air that can be aspired forcibly beyond the tidal volume. And what that means is after a normal breath in, if you inhale as much as possible after that, that extra amount of air that you can inspire or breathe in, that's your reserve volume for that, or your reserve inspiratory volume. Your expiratory reserve volume is the amount of air that can be forcibly expelled from the lungs. So after a normal breath out, if you then push all of the air that you can out of your lungs, that's the extra air you can breathe out, or the reserve expiratory volume. And then the residual volume is the amount of air that never leaves your lungs. It stays inside those conducting zones and in the respiratory zones. It's needed to keep those alveoli open. If you combine two or more respiratory volumes, you get a respiratory capacity. Their equations are here, but it's much easier to look at them in a chart. With this chart, I can tell that in order to calculate inspiratory capacity, I would need to add IRV and TV together because the bracket is going to be around both inspiratory reserve volume and tidal volume. If we look at another one, total lung capacity includes in its bracket all four respiratory volumes. So if you add all four respiratory volumes together, inspiratory reserve volume, tidal volume, expiratory reserve volume, and residual volume, you would get total lung capacity. Here are the definitions for the respiratory volumes and respiratory capacities. Be familiar with these definitions in general, especially those for the respiratory volumes. We also want to talk about anatomical dead space, alveolar dead space, and total dead space. The anatomical dead space is the air that remains in the conducting zone. This air never contributes to gas exchange, so it never makes it to those respiratory zones. Alveolar dead space is air that may make it to the alveolar areas, those respiratory zones, but it's going to be in a non-functional space or a non-functional alveolus. So due to collapse, obstruction, for some reason, this alveolus is going to be non-functional and doesn't participate in that gas exchange. And the air there is the alveolar dead space. If you add the anatomical dead space to the alveolar dead space, you have the total dead space, which is the sum of both. Spirometry can also distinguish between different types of pulmonary disorders. One would be obstructive pulmonary disorders, the other restrictive pulmonary disorders. Restrictive pulmonary disorders decrease or reduce lung compliancy by reducing total lung capacity. Introducing scar tissue or some type of fibrosis could decrease how stretchy the lungs are, and this would be a restrictive disease. So lung expansion is compromised in a restrictive pulmonary disorder. Obstructive pulmonary disorder is when inflammation or mucus or something restrictive is introduced into the bronchial tree. Restrictive in the sense that it introduces resistance, not that it decreases lung compliance. So bronchitis or inflammation of the bronchi is a great example of an obstructive pulmonary disorder. Pulmonary function tests can also measure the rate of gas movement. For this, forced expiratory volume is a little bit better than forced vital capacity because forced expiratory volume is over a specific time interval, which is representative of a rate. And so forced expiratory volume is the amount of gas expelled during a specific time, not just after one breath, which is what forced vital capacity is. Minute ventilation and alveolar ventilation rate can measure ventilation. Alveolar ventilation rate measures effective ventilation because it's looking at the flow of gas all the way into those respiratory zones, into the alveoli in a particular time. Whereas minute ventilation is not necessarily looking at that gas getting to the respiratory zones. It's instead just looking at how fast gas gets into and out of your respiratory tract. And there's no guarantee that that air in that amount of time was able to get into your alveoli. So a better measurement of effective ventilation is alveolar ventilation rate, or AVR. Rapid shallow breathing can actually decrease AVR because if you reduce the depth of breathing, you are going to reduce the amount of time that air has to get to those alveoli or the ventilation spaces. So rapid shallow breathing can actually decrease AVR, whereas slow deep breathing gives more time for that air to get to those alveolar spaces, and that will increase AVR. And that's what we're seeing in this chart. We have the normal rate and depth of breathing. The AVR for that is 7,000 milliliters per minute. It increases with slow deep breathing and decreases with rapid shallow breathing. Next, we want to look at gas exchange. We have two types of, or locations rather, for gas exchange. External respiration occurs between the blood and the lungs. Internal respiration occurs between the blood and the tissues. External respiration, therefore, is sometimes called pulmonary gas exchange, whereas internal respiration is sometimes called tissue gas exchange. Both processes are going to be subject to the basic properties of gases and the composition of alveolar gas. So we'll look at both of those. To look at both of those, specifically starting with the properties of gases, we have to introduce a couple of laws. The first is Dalton's law of partial pressures, which says the total pressure exerted by a mixture of gases is equal to the sum of its partial pressures. So the gas we breathe is made up of nitrogen, carbon dioxide, and oxygen, and each one in different amounts. The gas that is present in the highest amount has a higher partial pressure than the other gases, but all the gases that make up air have a partial pressure, and if we add them together, we get a total pressure. So the pressure exerted by each gas in a mixture is a partial pressure, and that partial pressure is going to tell us how much of that gas is in the mixture compared to others, because it's going to be directly proportional to its percentage in the mixture. So here we're looking at nitrogen and oxygen, which make up the air we breathe. There's a little bit of carbon dioxide, and we can see the calculations of partial pressure based on the amount of that substance, of that gas, in the air we breathe. So we can see that nitrogen makes up more of the air we breathe than oxygen, and their calculations for partial pressure reflect that. So nitrogen has a higher partial pressure than oxygen. There's also carbon dioxide, water vapor, and some other gases in the air we breathe, but to an extent these are insignificant. We would see that partial pressures decrease at high altitudes, but they're going to increase underwater. We'll look at this in more detail in a later slide, but this chart is showing you that there is more carbon dioxide in the alveolus than in the atmosphere, and there is more water, specifically water vapor, in the alveolus than in the atmosphere. Moving on, we want to look at Henry's law. Henry's law is for gas mixtures that come into contact with water or liquids, and the gases will dissolve into a liquid better if they're in higher proportion in a mixture or they have a higher partial pressure. The amount of gas that dissolves into a liquid depends on its solubility or ability to dissolve, and carbon dioxide is going to be 20 times more soluble than oxygen. So it's more likely for carbon dioxide to dissolve at a liquid-gas barrier than it would be for oxygen. So what we're going to see here is that in order for carbon dioxide to move from an area of high pressure to low pressure, the difference in pressures doesn't have to be that great because carbon dioxide likes to dissolve into a liquid. But for oxygen, it doesn't like to dissolve into a liquid. So for it to move from an area of high pressure to an area of low pressure, the difference in pressures on each side of this boundary must be tremendous. It must be a great pressure gradient. Another thing that this would depend on is the temperature If you increase temperature, you decrease solubility, because if a gas is introduced to higher temperatures, it becomes even more gaseous. The molecules move about more, and it's much harder to consolidate them into an area that can then dissolve into a liquid. A quick homeostatic imbalance we'll talk about is oxygen toxicity. So breathing oxygen at a partial pressure higher than 3 atmospheres is dangerous because it can create free radicals, and free radicals can mutate your DNA. Other things that can occur are central nervous system disturbances, coma, and even death. So I finally got to the slide where we're going to talk about alveolar gas. We saw a chart a couple of slides back that said that the alveoli contain more carbon dioxide and water vapor than atmospheric air. And the reason that is because of gas exchange. During gas exchange, oxygen is going to diffuse out of the lung and into the blood. So oxygen very quickly leaves and goes into the blood so it can go to tissues. And carbon dioxide is going to diffuse into the lung. So we're going to have more CO2 in the alveolus because CO2 is coming from the blood to the lung at this pulmonary gas exchange location. We're also going to see that the humidification of conducting zones to that air that is passing through them has brought water vapor to the alveoli. So the humidification of air by conducting passages is the reason there is more water vapor in the alveoli than there is in the atmospheric air. And there's just constant mixing of the alveolar gas as well. We're constantly breathing in and breathing out, bringing in newly inspired air, and then breathing out the air that's come from the tissues. It includes a lot of CO2. So that mixing of alveolar gas is another reason for the composition of alveolar gas. Next, we want to look more in detail at external respiration. Again, external respiration occurs between the blood and the lungs. It's also called pulmonary gas exchange. During external respiration, we're going to exchange the two respiratory gases, oxygen and carbon dioxide. Oxygen will go from the alveolus or airspace into the blood, and CO2 will move from the blood into the alveolus or airspace. Both of the respiratory gases are moving across a respiratory membrane, which is very thin and made up of alveolar endothelium, capillary epithelium, and a fused basement membrane. Other things that can influence this exchange is partial pressure gradients and gas solubilities. So we'll talk again about those gradients between oxygen and CO2, as well as the solubilities of CO2 and oxygen. The thickness and surface area of respiratory membrane. The respiratory membrane needs to be really thin in order for gas exchange to occur via diffusion. And we'll see that ventilation-perfusion coupling is important for making sure that airflow matches blood flow. So first we'll look at the partial pressure gradients. There is a really steep partial pressure gradient for oxygen because it doesn't like to dissolve into fluid. So in order to get oxygen to go from the airspace to the blood, the difference in pressures on each side of that boundary, the respiratory membrane, must be tremendous. And we see that it is. Here we have the partial pressures of oxygen in both venous blood and the alveolus. In the alveolus, there is 104 millimeters of mercury of oxygen. That's its partial pressure in the airspace, which is much larger than the partial pressure of oxygen in the venous blood. The venous blood that is coming to the lungs and entering into the pulmonary capillaries. So what we're seeing for the venous blood, its partial pressure of oxygen is 40 millimeters of mercury. So there's a lot of oxygen in the airspace, not as much oxygen in the blood or the pulmonary capillaries. And this steep difference is going to ensure that oxygen is able to go from the airspace to the blood during external respiration. So we need a steep gradient because we want oxygen to flow into the blood, but oxygen does not like to dissolve. We also see that this steep gradient makes oxygen exchange really quick. Equilibrium of gas exchange is reached in 0.25 seconds, and blood actually is able to pass through the pulmonary capillaries in about 0.75 seconds. So in a third of the time it takes for red blood cells to pass through the pulmonary capillaries and participate in gas exchange, we've already gotten oxygen to flow into the blood. So if for some reason blood flow slowed, we could still get adequate oxygenation of the blood. The partial pressure gradient for carbon dioxide is a lot less steep. Carbon dioxide likes to dissolve in fluid, so we don't have to have a pressure difference that is that tremendous or that different. So we can see that in the blood, there's 45 millimeters of mercury for the partial pressure of carbon dioxide, whereas for the alveolus or airspace, there's a partial pressure of carbon dioxide of 40 millimeters of mercury. What we're looking at here is there is more carbon dioxide in the pulmonary capillaries than there is in the airspace. So if we follow pressure gradient rules, we're going to see that carbon dioxide moves from an area of high pressure to an area of low pressure, or it's going to move from the blood to the airspace. And that completes what occurs with the respiratory gases during external respiration. During external respiration, oxygen moves into the blood, carbon dioxide moves into the airspace. And we can see now this is because of both the solubility of these gases and their partial pressure gradients. So for CO2 here, even though the gradient's not steep, carbon dioxide is still diffusing in equal amounts with oxygen because it's 20 times more soluble in plasma than oxygen. This image shows us the partial pressures of oxygen and CO2 at the lungs, specifically in the air spaces, and we can also see the partial pressures of oxygen and CO2 in the blood that's leaving tissues and will eventually be coming to those air spaces via the pulmonary capillaries. So this image just represents those partial pressures that were talked about in the 2 slides previous. Here we can see that the time that blood spends in a pulmonary capillary is almost 3 times longer than it needs to become oxygenated. So here we have deoxygenated blood, here we have oxygenated blood, and it only took about 0.25 seconds for this blood to get the oxygen it needs. So even if blood flow sped up 3 times as fast, we'd be able to get enough oxygen into our blood. Another factor that could affect respiration is the thickness or the surface area of the respiratory membrane. It's important that the respiratory membrane, which is made up of the capillary epithelium, the alveolar endothelium, and a fused basement membrane, be very, very thin. If it wasn't thin, we wouldn't be able to have gas exchange via diffusion. So it's about 0.5 to 1 micrometer thick, and that's thinner even than tissue paper. It's also important that we have a lot of alveoli and that their convoluted space provides a lot of surface area for gas exchange. If the respiratory membrane were to thicken, maybe because the lungs became waterlogged or fluid built up between the epithelium of the capillaries and the epithelium of the alveolus, that could result in decreased gas exchange and interfere with the oxygenation of tissues. So pneumonia or left-sided heart failure could be imbalances that cause waterlogged lungs or edematous tissues, that word got me, or edema in tissues near the respiratory membrane. So even though that 0.75 seconds gives us a little bit of leeway for the time it takes for diffusion to get oxygen into that blood, conditions such as pneumonia and left-sided heart failure could still interfere with this gas exchange and make it not adequate enough. And this again would cause body tissues to suffer from oxygen deprivation. There's also pulmonary diseases that can reduce alveolar surface area by destroying alveoli. Emphysema is one of those disorders. It would actually break down the walls of the alveoli, decreasing the convolutions we would find in an alveolar sac, and therefore decreasing alveolar surface area. Tumors, mucus, and inflammatory material could also do this as well. They would do this, however, by blocking alveolar structures. So here we see normal lung on the left. We see a lot of convolutions, a lot of air spaces, and those convolutions and increased amounts of alveolar epithelium introduce or create a bunch of alveolar surface area. If you destroy those convolutions, that decreases alveolar surface area, and that can also decrease gas exchange at the lungs. So we see a lung with emphysema on the right, and we see that it doesn't have as much surface area as the lung on the left. Another thing we want to match up during external respiration is blood flow with gas flow. Perfusion is blood flow reaching the alveoli. Ventilation is the amount of gas reaching the alveoli. And we want to send the blood where there's oxygen. So if there's no oxygen in an alveolus, we don't want to send the blood there. So for that purpose, we're going to match perfusion and ventilation. And this is called ventilation-perfusion coupling. Both are controlled by local autoregulatory mechanisms, so this will include either the constriction or dilation of arterioles or bronchioles, and they're controlled by different chemical measures, and those chemical measures are going to be the partial pressures of the respiratory gases. If there's a change in the partial pressure of oxygen in the alveoli, we're going to see that this affects the diameters of arterioles. If there is a higher partial pressure of oxygen in an alveolus, that's going to cause the arterioles that go to that alveolus to dilate. That way, blood flow arrives at the alveolus that has a lot of oxygen. If the partial pressure of oxygen in an alveolus is low, that's going to cause the arterioles that go to that alveolus to constrict. And if they constrict, we're going to route that blood flow to another location that hopefully has high oxygen levels, unlike this alveolus that has low partial pressure of oxygen. So what we're doing is directing blood flow by constricting or dilating arterioles. And this is the opposite mechanism that we saw in systemic arterioles. In systemic arterioles, we saw dilation when we wanted oxygen to go to an area, and we saw constriction when we had a lot of oxygen at that tissue and we didn't need to send oxygen to that area. For the bronchioles, it's going to be the amount of CO2 that causes their constriction or dilation. Where alveolar carbon dioxide amounts are high, the bronchioles dilate, meaning that if there's a lot of CO2 in an airspace, the bronchioles will dilate or open up so that that CO2 can escape easier. Where alveolar CO2 is low, meaning there's not as much CO2 in that airspace, the bronchiole will constrict. It'll bide its time until there's more CO2 in that airspace, and so it will not open up to allow that CO2 to escape quickly because it's not as abundant and doesn't need to escape like the high CO2 situation did. And this just allows elimination of CO2 more efficiently and rapidly. Again, we want to balance ventilation and perfusion, so we'll see diameter changes for bronchioles and arterioles in order to match up ventilation and perfusion. This is not always completely balanced, however, even though we are trying to couple the two processes, because there are gravity variations in blood flow and airflow, and sometimes alveolar ducts get plugged via mucus or because of inflammation. This is a good image to study because we can see that here we have an alveolus that is collapsed, so it doesn't have a lot of airflow, maybe not a lot of oxygen, but there's a lot of blood flow going to this airspace, so they don't match. We have low oxygen or low ventilation and high perfusion. But if the arteriole constricts, we will have coupled or matched up ventilation and perfusion. Now we have low ventilation and low perfusion. Over here on the right, so example B, we have high ventilation and low perfusion. But if the arteriole dilates, we will have matched up ventilation with perfusion. And one of our last topics is going to be internal respiration. Internal respiration is essentially the opposite of external respiration, and we also want to remember that it happens in a different location. So external respiration happens between the blood and the lungs, whereas internal respiration happens between the blood and the tissues, and is also called tissue gas exchange. During internal respiration, oxygen is going to leave the blood and go into tissues, and that is because tissue partial pressure of oxygen is always going to be lower than that in arterial blood. And then we're going to see that carbon dioxide moves from tissue cells into the blood, and that is because the partial pressure of carbon dioxide in tissue is always higher than arterial blood. And so for internal respiration, we will have oxygen unloading from the blood and CO2 loading into the blood. And this is happening again at the tissues, whereas external respiration happened at the lungs. And we see the same image again, but this time we're going to look at the partial pressures of blood leaving the lungs and the partial pressure of the air at the tissues. So we see the respiratory gases in both locations, and we can see that we have favorable partial pressures for oxygen leaving the blood and going into tissues, and carbon dioxide leaving the tissues and going into the blood. And that's it for Part B of Chapter 21 over the respiratory system. We'll move on to Part C next.